Okay, so hi everybody. Today I want to talk about the moons in the outer solar system. That is, these objects that are in orbit around Jupiter, Saturn, Uranus, and Neptune. Now, we've already talked a little bit about these objects where we pointed out that they're comparable in size to Earth's moon or the planet Mercury. Now, based on that, you might assume that these are mostly geologically dead worlds. Like Earth's moon, their surfaces are fairly ancient because they've lost all of their internal heat. And that's a reasonable supposition given their size. They're small enough, and many of them are mostly ice, that they would have lost their internal heat fairly quickly. But it turns out that this collection of moons includes several active bodies that are actually geologically active today. This includes Jupiter's moon Io, Saturn's moon Enceladus, and Neptune's moon Triton. It also turns out that Jupiter's moon Europa may be active today and was definitely active in the recent geologic past. Also, at the same time, there is Titan, whose surface is distinct in a number of other ways. I want to focus our attention on these objects because they demonstrate how objects can be active and or interesting despite having lost a fair fraction of their initial internal heat. So to start that discussion, let's consider the Galilean satellites. These are the four big moons of Jupiter, which are named Io, Europa, Ganymede, and Callisto. These objects are interesting to look at first, both because they're from the closest giant planet to us, but also because they provide an interesting trend, which we will see that activity depends on distance from the planet. So let's first look at Callisto, the outermost of Jupiter's large satellites. Callisto's surface is dominated by impact craters. This is a close-up picture of Callisto, and all of these circular splotches, even this really big one, are basically impact craters. So Callisto's surface does indeed appear to be ancient and is mostly just heavily cratered. Working our way inwards, we find Ganymede. Ganymede's surface is also fairly heavily cratered. This is a close-up view of Ganymede's surface. And there's this region here, which is actually quite highly cratered. But there are regions like these bright bands, part of which is shown here, which are clearly tectonic, where the surface has been pulled apart. And these regions, while they have craters, are slightly less heavily cratered. This suggests that Ganymede had some amount of geologic activity at some point in its past. Also, Ganymede has an intrinsic magnetic field. So kind of like Mercury, Ganymede is probably largely geologically dead on its surface at the moment. There isn't much geologic activity or volcanism, but its interior still has some amount of heat. Going even further in, we next hit Europa. Europa's surface has very few craters. Its surface is covered in ice, and that ice is heavily fractured. All of these lines you're seeing are basically fractures. They're tectonic features in the ice. And this suggests that its surface is being constantly reworked. There are hints that Europa might be even geologically active today, but it's definitely been geologically active. Its surface has been refreshed in the recent geologic past. How recent that is a matter of some debate. Finally, we have Io, which is the most geologically active object anywhere in our solar system. If you look at a picture of Io, you see it's covered with various splotches. Those are not impact craters. Every one of these splotches is a volcano. And these are not volcanoes that are active in the geologically recent past. Almost all of these things are active today. This is a picture of Io. This is a volcano. This is a volcano. This is another volcano. Volcanoes are going off on Io all the time at a prodigious rate. You can see in the infrared, various of these caldera are just glowing. This thing is amazingly active. So this is a really dramatic trend. The moon closest to Jupiter is extremely active. The moon furthest away is less so. This implies there's some connection between the activity of these objects and something about the planet. And this is in fact the case. These objects, especially Io, are geologically active due to their gravitational interactions with their host planet. And how does this work? Well, the fundamental process that is responsible for making these volcanoes on Io and producing activity on Europa and maybe Ganymede is what is called tidal response. It's the same basic process that allows the moon to raise tides on Earth. The thing is, if you have an object like the moon that's close to another object like the Earth, the fact that gravitational forces fall off like distance squared means that the gravitational pull of the moon on different parts of the Earth is different. Specifically, the gravity of the moon pulling on the Earth, which does affect the motion of the Earth, is a little stronger just beneath the moon than it is at the center of the Earth. What that ends up doing is that it causes water, particularly, to flow towards the moon. Now, at the same time, water also flows to the side of the Earth away from the moon. What's happening here? Well, the gravitational pull of the moon on the center of the Earth is a little stronger than the gravitational pull of the moon on this bit of water. So the moon's gravity is a little weaker there. So the fact that the Earth is being pulled a little bit by the moon, and the moon orbits the Earth, but the Earth also reacts to the moon, means that basically that pulls the Earth a little away from the ocean, creating another high point here. And this is fairly typical. The gravitational pull of the moon creates what are called tidal bulges. It creates two regions of high tide, one directly under the moon, one 180 degrees away. It also creates two regions of low tide, here and here. Now, this is happening in Earth's oceans where we can see it most clearly because oceans don't have any strength. Water just flows to where it wants to go. And this is, of course, highly exaggerated. The motions of the oceans is not that much. But it does happen. And the thing is, this doesn't just happen to Earth's oceans. It also happens to rock. Rock has strength, so it doesn't flex as much, but it does flex some. So if you have a moon in orbit around a planet, it also gets stretched a little bit. Again, this is not to scale. And that means that it tends to have a long axis that points at the planet, which is interesting and in fact true for Earth's moon. If you measure the shape of the moon, it's slightly longer in this direction than it is to this one. Now remember, Earth's moon is a synchronous rotator. That means the same side of the moon always faces the Earth. Now, we can actually get a sense of why that is. Let's imagine that the moon didn't do this. What if the moon was rotating at a different rate? So that, what would that do? What that would do would take that bit of the moon that's extended towards the planet and cause it to tilt away. Well, what will happen then? Well, the Earth would pull back on that thing, slowing it down, causing it to, trying to get it back into this aligned configuration. This aligned configuration is the stable endpoint of the moon's rotation state. If it's going too fast, it'll get slowed down to this state. If it ever got slower than this, it would be sped up into this state, because this allows the moon to just keep its long axis, regardless of how it was formed, pointed at the Earth. And this is why all of these moons, Io, Europa, Ganymede, and Callisto, have the same property. They have a long axis that points towards the planet. And this is perfectly nice, stable equilibrium configuration as long as the orbit is circular. But if the orbit is eccentric, this is actually a problem. Because if the orbit is eccentric, the rate at which the object moves around the planet changes. It moves a little faster when it's near pericenter, when it's closest to the planet. It moves a little slower at apocenter, when it's furthest from the planet. But the moon has to rotate at a single rate. It can't speed up and slow down once in orbit. So what that means is that at certain times, the moon gets tilted with respect to the planet. So as it's moving in, and at this point, it's falling slightly behind. So this diamond is a little off center. Now it's moving too fast. And so the diamond gets a little off center here. What that means is the moon is wobbling slightly relative to the planet. So it's being pushed back and forth once in orbit. Basically, the planet's gravity is squishing and squashing the moon a bit. It's taking the moon that was nicely aligned and rolling it back and forth. And just like if you took modeling clay and rolled it between your hand, it gets a little warm because that crushing and squeezing force gets turned into heat. Turns out that's what's happening to Io. Io's orbit is eccentric. It is doing this. And this is what is responsible for making Io extremely volcanically active. Its orbital eccentricity is high enough, and those squeezing forces from Jupiter, which is a very massive planet, are big enough to produce this sort of geologic activity. But that raises a question. Why is Io's orbit eccentric? It turns out that that type of wiggling tends to get rid of eccentricities. So that kind of energy gets dissipated, and eventually you settle down back to a circular orbit. Io's not in the circular orbit. It hasn't completed this process. Why hasn't it? This is something that should happen relatively quickly over geologic timescales, but it hasn't. And the reason it hasn't is because of how Io is interacting with Europa and Ganymede, these other two moons. Io, Europa, and Ganymede are in what is called an orbital resonance. That is where the orbit period of one of these ratios is a whole of the orbit period of one of these moons is a whole number times the orbit period of another moon. So in particular, the time it takes Ganymede to go around Jupiter once is also the time it takes Europa to go around Jupiter twice, and the time it takes Io to go around Jupiter 4 times. This is what's called a 1 to 2 to 4 resonance. Now, to get a better picture of it, it's nice to look at an animation. What I'm going to say is watch these moons as they go around. We're going to watch Ganymede. Ganymede goes around, doo-dee-doo-dee-doo-dee-doo. Now watch Io. Io is going around once, twice, 3 times, 4 times in the time it took Ganymede to go around. And you can do similar comparisons. This is not just numerology. This has physical consequences. To see what those physical consequences are, it's useful to look at just a simple situation. Let's consider a planet with 2 moons, one with an orbit period of 4 days, one with an orbit period of 8 days. These are none of Jupiter's satellites. This is just there with whole number of days to make things simpler. Now, this moon is closer to Jupiter. It goes around faster. It has a shorter orbit period. This one has a longer orbit period. What that means is that at some point, at some time, which we'll call time 0, the moon will pass the other moon. The inner moon will pass the outer moon. This is when the inner moon gets as close to the outer moon as it ever does. This results in a little extra gravitational tug towards that moon, which changes its orbit somehow. If before this encounter, the moon was on a circular orbit, it would be a little eccentric. Exactly how that eccentricity would work, we can leave that aside. After this encounter, which will mark as t equals 0 days, this moon moves ahead of this moon because it's on a faster orbit. So one day it's now pulled ahead. It's now getting further ahead, still further ahead. After 4 days, it's completed an orbit, but now the moon is on the other side. The other moon is on the other side, so it just keeps going. 5 days, 6 days, 7 days, it's coming up on the other moon again. After 8 days, it has another encounter. But the important thing to note is that this encounter is happening at the same place in the orbit as the previous encounter. So whatever this moon did to this moon's orbit, it's going to do it again. So if the first encounter stretched the orbit a little bit this way, it would stretch it again. This happens because their periods are a whole number ratio. It means that the orbit keeps getting stretched in one direction. If there wasn't this whole number ratio, sometimes the orbit would be stretched one way, then it would be stretched another. It would average out to nothing. In this case, the perturbations from the moon can build up and lead to significant eccentricities. Now, in this cartoon example, the orbit distortions from each encounter were large. In practice, they're very small. But because of the resonance, it allows these different moons to interact. And this drives up Io's eccentricity to a level where it becomes volcanically active. So that interaction amongst these 3 moons is what is allowing Io to stay in an eccentric orbit and allowing Jupiter's tides to produce its high level of activity. Io is trying to dissipate its eccentricity by becoming a more circular orbit, but its interactions with Europa and Ganymede are preventing that from happening. This is why Io is as active as it is. Now, that same mechanism is also maintaining Europa at a finite eccentricity. It's further from Jupiter, so the tidal forces aren't as strong, but it is being affected. And that can drive activity, but it's not nearly enough to produce normal volcanoes. Instead, it seems to be causing Europa to erupt water. There is hints that Europa is active. This comes from various images taken by the Hubble Space Telescope. This is a picture of Europa silhouetted against Jupiter, and you can see there's some dark patches here. This might be stuff erupting from Europa, specifically water vapor. Now, the thing is, Europa, its density is mostly rock, but it's covered in ice. Those tidal forces probably aren't enough at Europa to melt rock, but it's enough to melt water. So outside the rocky center of Europa, there might be a layer of liquid water. In fact, given how Europa interacts with Jupiter's magnetic field, there kind of has to be. So even though Europa's activity level is well below that of Io, it is able to have a relatively fresh surface because of what it's made out of. Now, at the same time, this raises a completely new way to think about habitability. Europa is not the only moon that might have a layer of liquid water inside it. Both Ganymede and Callisto may as well. The evidence for those is a little more ambiguous. But this is an environment where we would have liquid water, we have energy, which is in the form of tidal interactions or maybe residual heat, and we could have nutrients in the form of organics or various rocks. So there are reasons to think that these internal oceans in these bodies could be habitable environments. This is kind of different from what we were thinking of Mars. Mars could have had a habitable environment sometime in the past that then may or may not have survived to the present day. These could have habitable environments today. The trick is they're buried under ice. So how do we access them? This is one of the reasons why activity on Europa would be interesting, because it might mean some of that habitable environment is leaking onto the surface, which would be helpful. This is part of the reason why we have a couple of spacecraft currently being planned to head off to the Jupiter system. NASA is planning to send a spacecraft called the Europa Clipper, whose job it is to probe this subsurface ocean and understand its habitability. How deep is it? What is its conditions? Is there material on the surface that could tell us its chemical environment, etc.? At the same time, the European Space Agency is sending a mission to Ganymede, which is a moon that's slightly easier to get to, but also has a relatively complex interior that may also, and probably does, harbor another liquid water layer. So this is a major goal for the next stage of Jupiter exploration. Now, Moving further out in the solar system, we can look at the moons of Saturn. Now, Saturn has a lot of moons. Many of these moons are ancient, geologically dead, we think, objects. They're things like Rhea or Dione or Iapetus. They are heavily cratered. Even Mimas, which is a smaller moon, is also pretty heavily cratered. This is consistent with what you kind of expect. They're small bodies, mostly made of ice. They probably lost their internal heat quite quickly. They're just been hammered for some number of years. An exception to that is Enceladus. Enceladus is a tiny moon. It seems like it should have lost its heat quickly. But if you look at Enceladus close up, while there are some regions that are covered with craters, there are other regions with very few craters, and its south pole in particular has no craters at all. Instead, it has a series of fissures on it. And those fissures are surprisingly warm. If you look at this region in the thermal infrared, the temperatures of these fissures are elevated, here indicated by color. The peak temperatures in the highest resolution data are high enough to be close to the freezing point of water, which is surprising because the background temperature this far from the sun is about 330 degrees below 0 Fahrenheit. And more than that, these cracks are not just fissures, they're geysers. There is actually material erupting from the surface. That's what you're seeing here. What's erupting? It's a combination of water vapor, solid ice particles, along with particles containing salt and organics. This is a geologically active world, again, where the activity is dominated by water. Now, what's going on here? Well, it's probably kind of like how Io is active. Enceladus is on an eccentric orbit, probably partially generated by its gravitational interactions with the larger moon Dione. That interaction may be powering enough internal heat to give Enceladus a subsurface ocean. And in fact, there's evidence for that. Again, based on careful study, there does seem to be a global ocean beneath the surface of Enceladus. So again, we have a combination of energy in the form of this tidal flexing and water in a liquid form. Furthermore, the material coming out of this crack has organic molecules in it. This is another potentially habitable environment. And what's really exciting about this is we can sample that environment because unlike the oceans on the Jovian moons, which are pretty deeply buried, this one is venting into space. So there have been proposals to launch missions that would sample that material and see whether there's anything living in it. So that's another interesting object for study. The other moon of Saturn that is worth studying is Titan, which is the largest of Saturn's moons. Now, Titan also probably has a subsurface ocean, just like Callisto and Ganymede do. But that's not what makes Titan so special. Titan is special because it has an atmosphere. This is what Titan looks like if you take a normal picture of it. It's a fuzzy orange ball. And that's not the surface. That is the atmosphere, which is denser than Earth's atmosphere and contains nitrogen along with a mix of hydrocarbons, methane, ethane, acetylene, propane, all sorts of things that form basically smog. That's what you're seeing here. The only way you can see through that smog, like at Venus, is look at either the infrared or at radio wavelengths. That's the only way you can see through the atmosphere, and you can start to see surface features. The other way to get through the atmosphere is to send a spacecraft through the atmosphere, which happened in 2004. There was a spacecraft called the Huygens probe, which landed on Titan. As it came down, it saw this terrain, which is a bit surprising. This looks like a river channel. And when it got to the surface, this is the scene around it. These look like river cobbles. They're eroded. Erosion is happening on Titan. Interesting. That suggests something is flowing on its surface. Later observations by the spacecraft revealed that this erosion is ongoing because at the northern pole, also a few at the southern pole, there are literally lakes and seas. There are regions at certain altitude where basically the surface is remarkably flat. And this was flat to the radio antenna. These are regions shown in black here. It was, and in fact, they were so flat, you could see sunlight glinting off of them. This is an image in the in the infrared, and you can see one of those lake-like regions and the sun literally reflecting off of it. These are true seas. They are filled with a liquid. That liquid is not water. At the temperatures of the surface, water is completely frozen. What you're seeing here are lakes and seas of natural gas, methane and ethane. That means what we're seeing here is something like our terrestrial hydrological cycle, but instead of having water as the fluid, we have hydrocarbons as a fluid. So we're able to see erosional processes like that work at Earth, but in a very different chemistry. And the whole chemistry of Titan is bizarre. If we look at other regions of Titan close up, we see this sort of structure. These are sometimes called cat scratches, but what they are dunes, like we would see in the deserts here on Earth made out of sand. But looking at the spectra of these regions, this isn't sand in the sense of what we think it is. It is complex solid hydrocarbons that is moving around like sand. So these would be small sand-sized grains of solid hydrocarbon. Now, life as we know it can't work here. Whether life as we don't know it could work here, that's an open question. But definitely there's a lot of interesting chemistry going on here. And one of the questions is, what exactly is going on here? Because chemistry involving hydrocarbons on Earth is basically all down to life. This would be potentially what does chemistry look like with carbon, hydrogen, and oxygen in an environment without life or with very minimal life? This is a different sort of thing to study, and it's something that is going to be explored by the Dragonfly spacecraft. This is a mission that does something rather remarkable. It is going to bring a nuclear-powered octocopter to Titan that will land on the surface, measure various things about the chemistry of the surface, and fly to multiple sites. Now, having an octocopter on Titan sounds like science fiction. But it is a serious NASA proposal that has been funded and is planning to launch late this decade. And the reason it can happen is Titan has an extremely dense atmosphere and extremely low gravity, which makes it relatively easy to fly on. The standard statement is, if you could get to Titan and you could basically strap on a pair of wings and you could fly yourself just by waving your arms with appropriate extensions. So, and this one's goal is to understand that chemistry, what's going on here in a system that has a lot of the same building blocks as Earth, but a very different environment. Okay. The last of the moons I want to talk about is Triton. Uranus has a bunch of interesting moons as well. They're mostly kind of old. There are some that might be active or not. The data is very limited. Neptune's moon Triton is a special case. This is a picture of Neptune's moon Triton. If you look at this, you'll immediately notice there doesn't seem to be many impact craters on it. Its surface seems to be young. And that's a fair impression. The other thing I will draw your attention to are these streaks at the bottom. These are, at least in part, active geysers. One of these was observed to erupt during the time that Voyager flew by it. This is another active object. Now, this one's activity is slightly surprising because unlike the other moons we talked about, specifically Io and Enceladus, there is nothing else in orbit around Neptune that's nearly the size of Triton. So Triton does not have a ready source of tidal heating, and it's not that big. So its original internal heat probably would have dissipated by now, at least to the level that would be able to affect the surface. So something else is going on. And part of that is tied to the fact that this is not a normal moon. Triton is probably not something that formed around Neptune. All of the other large moons are in a state where they go around the planet in the same direction as the planet rotates. That's a typical configuration. Most of the moons of Jupiter, Saturn, and Uranus do that. Triton goes the other way. It goes around the opposite direction. That suggests that Triton is not one of Neptune's moons originally. It was something that was captured into the Neptune system sometime after it formed. In fact, what we think Triton is one of the largest objects from the Kuiper belt. That is that same group of objects that includes things like Pluto. And so at this point, it's worth comparing Triton to Pluto and also Pluto's moon Charon. These objects all show kind of a surprising amount of geologic activity, especially compared to the objects found closer to the sun. If we look at objects in the size range around Jupiter, Saturn, and Uranus, what we see are heavily cratered bodies. But out here, we see Triton, which doesn't have many craters. We can see Pluto, which has regions that are decently cratered, but other regions like this part, which have basically none, and other things. And furthermore, both Triton and Pluto have atmospheres. They're fairly tenuous, but they do have atmospheres. So what's going on here? Are these objects particularly geologically active? Do they have a lot of internal heat? That's not really what's going on here. What's happening is that we're now in a part of the solar system that's so cold that new materials begin to participate in geology. The surface temperatures of both Triton and Pluto are only 40 Kelvin, so 40 degrees Celsius above absolute zero. At this point, water is a solid. But things like nitrogen or carbon monoxide, things we think of as gases, start to freeze. The low crater count region here in Pluto, this thing is a gigantic nitrogen glacier. The geologic activity on Triton also seems to involve nitrogen. Even though we're very cold, for both of these objects, we are near the boiling point of some of the materials that are frozen on their surface. So it doesn't take much heat to make things that are quasi-geologically active. We can actually see flows of material happening in this nitrogen glacier on Pluto. We potentially just heat up the surface a little bit on Triton and turn solid nitrogen or liquid nitrogen into a gas, driving eruptions. So turns out that at certain distances from the sun, geologic activity might become easier because of the materials involved. And this is one of the reasons these sorts of objects are particularly interesting these days. So that's the moons of the outer solar system with a special guest appearance by Pluto. Thank you much for your time and attention.